Hello, I'm Sean. I'm joined by my teammates Marcella, Noah, Robert, and Willem, and this is the analysis and redesign of a string trimmer. So a string trimmer or weed whacker is used to cut weeds and grass in yards, and it's a motor used to spin a length of plastic cord in order to cut that vegetation. This is an exploded view of the original product that we will be redesigning. Our primary customers are homeowners who will use this to trim their own yards. Anticipated volume is about 100,000 units per year. And our secondary customers are lawn care companies who use these string trimmers for more full-time purposes with an anticipated volume of about 15,000 units per year.
For the functional analysis, we constructed a fast diagram for our weed whacker. The main function was to remove various forms of vegetation. This was performed by rotating the cutter and feeding different cutting material. The supporting functions would focus on user experience and results. The Fishbone assembly diagrams show two differing sequences. Sequence 1 starts with the upper assembly and assembles two halves of a motor following a lower and cutting end as the final step. Sequence 2 starts as the cutting head and follows with the upper assembly, a full motor assembly, and finishes with a rear and electrical assembly. Components comprise very small parts. We're consolidated here for simplicity. The function component matrix shows a task completed by the parts. There were 11 basic and supporting functions. The most used function was to maintain control. The most used part was the switch, and the least used part were the brackets.
Here we have the bill of materials, and as you can see, the bottom parts are all purchased separately, and those are highlighted in gray, and the top ones are all made by injection molding, machining, or extrusion. The most expensive part is the motor at $655, and then the total cost of the full assembly is around $33, which makes sense considering trimmers go between $40 and $100, depending on the platform and quality. This gives the manufacturing companies plenty of room to make a profit and falls within the expected range of the cost being between 40 and 70%. Here we have a quad chart, and as you can see, there are no parts that are listed as both high cost and low functional importance. However, we can eliminate some of the low cost and low importance parts, which will still help to minimize the costs. Another possibility is that two of the high cost and high functional importance parts could be combined to one part that still accomplishes both functions.
Comparing the functions for our primary and secondary customers, the functions differentiate with improving posture, increased ergonomics, the housing for the cutting material, and shielding debris. This is because we want to focus on the longevity of use when it comes to lawn care companies. Those string cutters are used for longer periods of time, so the ease of use and durability are the main differentiating factors. This is then seen in the component commonalities with the lower unit head, clamp, rear grip, and the shroud being the modules. For the product family assembly sequence, we modified it by moving the lower unit head and the shroud to the end of the assembly in order to have delayed differentiation and have all the platform components assembled before adding any of the modules.
Here we can see a few modifications that were made to the product family in order to better fit our customer groups. The lower unit head for the residential customers has a manually inserted string with a holder located on the cap of the assembly. The industrial unit head is filled with a standard mount for a spool of automatic feed string pictured to the right. Since the lawn care companies get a lot more use out of their string trimmers, they won't want to be wanting to replace the string manually all the time. Below that, you can see the different rear grip assemblies with a slightly tilted grip for the industrial customers, giving a more ergonomic design. Another change between product families is the addition of a strap holding clamp to the string trimmers for the secondary customers. This allows for a strap to be attached to the string trimmer, reducing the load on a user's arms for long work days.
The shroud was made modular for the second customer to promote user protection against debris. The overall shroud was enlarged and side guards replaced to increase protection for the lawn care company personnel who will encounter thicker vegetation as well as rocks and other forms of debris than the average user. The most common interface that was found were the tubes. The rear grip and clamp mounted the tube platforms, and the lower unit head and shroud mount to the lower unit. However, it's important to note that the lower unit also mounts to the tube platform. Therefore, the tubes were selected as a common interface, and the mounting points are indicated by ovals in the diagram. In our design for manual assembly analysis, it was found that the lower unit, shroud, and the brackets have the largest assembly time, which indicated a change for our shroud design as supported by the quad chart in the high safety performance function. The tube and bracket platform also called for a redesign or elimination from our quad chart, showed a low functional importance and a high assembly time. The lower unit was covered in DFA for automation, as well as our BOM indicating too many fasteners. Our overall efficiency was 13%. After design for manual assembly of the platform, brackets were eliminated, allowing for a reduction of parts, hence reducing fasteners from those parts and making the tube shorter by adding a locating feature. In our design for manual assembly of the module, fasteners were also reduced, hand and tool access was improved, and the locating features were also provided to aid in assembly of the shroud to the lower unit. After the redesigns were made, including elimination of the brackets, the shroud redesign, and less fasteners, the overall time for assembly was reduced by 79 seconds and increased the efficiency by around 10%.
For the redesign for automated assembly, we focused on the lower unit subassembly due to most parts in the subassembly being of high priority and of high manufacturing cost in the quad chart, as well as in the assembly, these parts make up the lower subassembly, allowing for automated assembly. We use the DFA design guidelines to make adjustments to the design. So for example, adding grooves to the lower tube to facilitate orientation into the lower unit head, which is defined by DFA 7, as well as adding locating features to the lower unit head for the shroud insertion, which is seen in DFA 11. And the analysis of these changes show that the total assembly cost goes from $40.47 to $33.99 due to the changing in the automatic handling code for the lower tube, as well as the insertion code improving for almost all other parts.
For our process selection for the lower unit head, it is made of high-density polyethylene, resulting in either machining or injection molding as our primary manufacturing processes. Both of these processes pass all of the different checks, so we chose injection molding as the final choice for manufacturing due to the very complex geometry that would greatly increase the cost for conventional machining. For the shroud, it is made of aluminum, so it could be die-cast, sheet metal worked, or machined. Based on the geometry, die casting was eliminated as an option, but sheet metal working and machining both pass all other choices. Due to the shape and bends of the part, sheet metal working was chosen as the final manufacturing process.
Looking at the design for manufacturing of the shroud, DfM Pro noted that there were multiple bends in different directions, as well as the bend radius being too small. We looked to improve this among other things, but one of the main goals was to minimize the setup and steps. The original, before any design changes, had 6 different setups for all of the different bins, whereas the after has just one setup for all of the bins. Similarly, we also wanted to avoid sharp corners, and we got rid of the locating tabs that were narrow features. And then we also added a slot for better alignment and assembly. These changes resulted in the total cost of the shroud decreasing by a little less than $3. Hubs had a similar comparison when extrapolated and with the 80% profit, and so we saw that as well.
Quite a few changes were made to the lower unit, although the overall structure was kept the same. Design for injection molding manufacturing rules were considered and resulted in a few major changes. The biggest consideration was removing side pulls, and this was done by removing undercuts in 2 locations indicated by the arrows in the top left of the right image. The higher arrows pointing to the screw hole in which the spaces for the nut and screw head were removed. This allows for only 1 side pull to be used in this location instead of 2. A draft angle was also added in between the 2 protrusions, which still allows the lower unit to be clamped around the base of the lower tube, but will give the mold an easier time when separating. Last major adjustments that were made got rid of most of the sharp corners on the part by adding fillets where possible. This will reduce flash production and give a much more consistent surface finish to the part. The changes made to the lower head had significant effects on the cost to produce the part. The formula for the cost of injection molding can be seen above and consists of material cost, operating cost, and mold cost per part. While the modifications for the lower head increased the total volume of the part and thus the material cost, significant improvements were made to the operating cost, which was mainly due to the reduction of the number of side pulls required for the mold to function. The original design required 4 side pulls and thus could only be formed with a single cavity mold. The modified part reduced the number of side pulls to only 2, meaning we could have a row of cavity molds. Calculations were performed with a 4 cavity mold and reduced the operating cost by almost 75%. This more complicated mold does cost slightly more, but is well worth it, as the modified part can be produced for less than 1/3 of the price of the original part.
For our services, we have 2 that we've developed. First is the Weed Whacker warranty. It's a 3-year warranty on all parts, and parts are made individually available to reduce machine downtime and reducing waste, allowing for refurbishment instead of fully replacing the unit. We also have a program called Whack Your Weeds. It's a subscription service where customers can share parts or full units with other customers, allowing for more use of these products. Finally, through this process, we've determined that we reduce the price of this product by almost $15. If we were to start the process over, we would look into improving the motor as well as reducing the weight of the overall product. Thank you, and we'll open it up to any questions.